Hello students, today we are going to discuss how haloalkanes can be prepared from hydrocarbons. By hydrocarbons we mean here alkanes and alkenes. So we'll begin with alkanes. Now it's a very important method. There are a lot of things to be understood, so I want you to be attentive right from the beginning of the video. So you know that when alkanes are mixed with halogen, which we have done in class 11 also, and the mixture is exposed to sunlight, then we get substituted alkanes. That means the hydrogens of the alkane get successively replaced by halogen. Now during this course of reaction we get mixture of products because none of the products formed is in sufficient quantity. If you remember, a few days back only we have discussed hydrocarbons from class 11, and the halogenation reaction we have discussed, that is methane when treated with chlorine and the mixture is exposed to sunlight. By sunlight here we mean H nu. We have represented sunlight by the photon H nu, or UV ray, or strong heating. Any of the three can be done. One of the hydrogens from methane gets replaced by Cl. So instead of CH4 you will have CH3Cl. But actually the reaction doesn't stop here. CH3Cl reacts further with another molecule of chlorine to produce CH2Cl2. And again it continues further reaction till all the hydrogens get successively replaced, and all these products formed, they remain in the reaction mixture. So none of the products formed are in sufficient quantity, and that is why it is not a good method to prepare a particular haloalkane. Okay, but however it is definitely a method, so we need to learn it. Now when we have similar hydrogens or similar carbons, by similar carbons what we mean, you look here we had only one carbon, so no question. When we have ethane, in ethane also we have similar carbon. By similar carbon what we mean, you see this carbon C, there are 3 hydrogens attached to it. Now when I look at the neighboring carbon, this C, it is also having 3 carbons attached to it. So this carbon having own hydrogen 3, neighboring hydrogen also 3. Now let's see the other way. Now let's consider this carbon. It has own hydrogen 3, neighboring carbon also 3. So both the carbons are having similar environment. So we consider them to be similar carbons and similar hydrogens. So one of the hydrogens from here will be replaced by chlorine. Remember, for our simplicity in studies, we are not considering the mixture of products. We are considering that product where only one hydrogen has been replaced by halogen. We call it monohalo product. So out of CH3, now we have one hydrogen replaced by Cl. So here we get CH3, CH2, Cl, and of course the byproduct is HCl. But the question is little difficult when we have different types of carbon and hydrogen, which is understood here. Let's try to understand very clearly, very important. Okay, you may see here I have labeled the carbons as A, B and A. Now what do we mean by A, B and A? You look at the first carbon labeled as A. How many hydrogens are associated with it? There are 3 hydrogens attached to it. So remember the number 3. In its neighborhood, how many hydrogens are there? 2. So remember the number 2. So I have labeled this carbon as A type because it has own hydrogen 3 and neighboring hydrogen 2. Now let us go to the second carbon, which I have labeled as B. Now in B what happened? In B what happened? Own hydrogen 2 and neighboring hydrogen 3 plus 3, 6. Is it same as before? Definitely it is not same as before, because earlier, if you remember, we had the 3:2. Now we have 2:6. So this is a different environment. We label it as B type. Now when we move to this again, which I have labeled as A, here also we find this carbon having 3 hydrogens of its own and 2 hydrogens in the neighborhood. So same as this. So this is also labeled as A. Now when I replace A type of hydrogen by Cl when treated with Cl, we get this product CH3, CH2, CH2, Cl. When we replace B type of hydrogen, what we get? CH3, CHCl, CH3. So two products are definitely not same. Now since the two products are not same, we have to understand which product is going to be the major product. Now the answer is based on stability of free radicals. For this you need to go back to the class 11 notes where we have done the stability order of various intermediates, free radicals, carbocations, carbon ions. So here you see the haloalkane which has been formed. What is the nature of this? This is 1 degree. And the haloalkane which has formed here is 2 degree. That means during the course of reaction, here a primary free radical formed, and here during the course of reaction a secondary haloalkane is formed, free radical has formed. Now if you go back again, if you try to remember, secondary free radicals are more stable than primary free radicals. As a result, second product is the major product and first product will be the minor product. You have to remember, as many type of hydrogens here we get, A, B, C, D, whatever types, that many products will be getting by substituting each type of hydrogen by the halogen. And from there we have to choose which product will be the major product. To understand which product is going to be the major product, you have to go back to the stability order of the free radicals, which we have done in class 11, and I have given you in the next page also. Here you may notice, here I have given you the stability order of the free radical. Methyl free radical is one of the weakest or least stable free radical, followed by primary, secondary and tertiary, and most stable free radicals are allylic and benzylic. Here we have not encountered allylic or benzylic free radical. Now question arises, if sometimes it may happen that I may encounter two different products, both are primary or both are secondary. In that case, how do I know which one is going to be major product? To understand this, we have taken this example. You can see here we have taken pentane, CH3, CH2, 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 CH3. Here we have three types of hydrogens because they are in different environment. Let us try to understand A type. In A type, what happens? This carbon is having own hydrogen 3. In the neighborhood it has 2. So let me write here 3, 2. So I have labeled it as A type. Okay. Next is B type. Own hydrogen 2, neighborhood 3 plus 2, 5. When you check the neighborhood, you have to look both right and left. When we have labeled the third one as C type, own hydrogen 2, neighborhood 2 plus 2, 4. And move to the next, which I again labeled as B type. You see own hydrogen 2 and neighborhood 5, same as this. Okay. And when the last one, that is A type, this one, own hydrogen 3 and neighborhood 2, same as this. So that's how we label them as A, B, C type. So how many products we are going to get? 3 products. When we replace A type of product, A type of hydrogen, we get CH3, CH2, 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 Br. Make sure here we have taken the halogen to be Br, and it will be a primary haloalkane. Clear? If I replace B type, the product which we shall be getting is CH3, CH2, CH2, CH, down you have to write Br, and then CH3. And this will be what type? This will be secondary. Third one, when we replace the C type, what shall we get? CH3, CH2, CH, down you write Br, then CH2, CH3. This is also secondary. Now if we are asked which product is going to be the major product, as you know, the answer will depend on the stability order of the free radical. So first product was primary, that is going to be the least amount. But B and C, by replacing B and C type, we got both secondary. Now how to know which one is going to be major product? You see, in B type what we had, 2 hydrogen of its own and 5 hydrogens in the neighborhood. In the C type we had 2 hydrogen of its own and 4 hydrogens in the neighborhood. In the neighborhood hydrogens we label as alpha hydrogen. Okay. Now go back to class 11 again. If you remember, we have discussed hyperconjugation, which states that more the number of alpha hydrogen, more stable is the species. So here we have 5 alpha hydrogen and here we have 4. So the one with 5 alpha hydrogen is going to be more stable product compared to the one having 4, though both are secondary in nature. So what will be the order of the products formed? A type will be least, followed by C type, followed by B type. Very, very important for you to understand this. Okay, so I have written the products here, you can check. I have labeled the product in such a way. You see, product A I have written by replacing A type of hydrogen. Product B I have written by replacing B type of hydrogen, and product C I have written by replacing C type of hydrogen. So here you can see here I have already given you the reasoning and all, everything is given here. Only thing is you need to read it once again and understand and listen to this video again and again. So there is a homework given to you, example 10.3, page 287 as per my book. Please work it out. I'm sure you are going to have difficulties, you are going to have problems in solving it, and I'll be very, very happy if some of you make an effort to send the work maybe after your unit test. All right. Next is an example of similar type. It is an in-text question. The question is asking you a similar question, that if you have this particular compound and if you have C5H12, and what are the different products you will be getting, different isomeric monohalo products if you do the free radical halogenation. So I have taken one of the first example given to you is 2,2-dimethyl propane, this one. Now how many types of hydrogens are there? Remember, whenever you discuss free radical halogenation, the first thing of yours is to identify the types of hydrogen. So let us do it. You look here, this carbon has 3 hydrogen of its own, no hydrogen in the neighborhood. So 3, 0. The other carbon, 3, 0, 3, 0, 3, 0. All of the carbons have 3 hydrogen of its own and neighborhood is 0. So all are equivalent here. So you may replace any one and get only one product. So the product which we got by replacing this one is CH3, C, and 2 CH3s up and down, and this CH3 becomes CH2, and in the place of the third hydrogen we get the chlorine. Okay. So that only one product we get here. With the same molecular formula, we get another structure, that is pentane, normal pentane, straight chain. Just now we have discussed this example and you can see we have got 3 products. Those 3 products are written here. The third one, they have asked you should get how many kinds of products? 4 kinds of products. So to get 4 kinds of products, what will be the structure? Same molecular formula, remember, but a different isomer. Now it is having 4 different types of hydrogen. How? Let us consider this, 3 hydrogen of its own, in the neighborhood 2. B type, 2 hydrogen of its own, 3 plus 1, 4 in the neighborhood. C type, 1 hydrogen of its own, 3, 3 plus 2 plus 3, altogether 8 hydrogens in the neighborhood. And D type, 3 hydrogen of its own, 1 in the neighborhood. You see, all of them, they have different environment. 3, 2, 2, 4, 1, 8, 3, 1. None of them are same. But if you look at this, 3 of its own and 1 in the neighborhood, that means this type. So this is also D type. So since there are 4 different types of hydrogens, we'll get 4 different products. Now look here, if this one A type, if I replace the hydrogen from here, this will give me a primary haloalkane. if I replace from here B type, I'll get a secondary haloalkane. If I replace from C type, I'll get a tertiary haloalkane. And if I replace from D type, I'll be getting another primary haloalkane. So the stability order will be definitely tertiary more than secondary. But out of two primaries, which one is going to be the major product? That will be decided by the number of alpha hydrogens. Okay, so here you see number of alpha hydrogens were 2, here number of alpha hydrogens were 1. So wherever we have less number of alpha hydrogen, that will be giving you less amount of product. So D product will be minimum, followed by A product, followed by B product, and C product will be in largest quantity. This particular portion is little tricky for you to understand initially, but you have to understand because lots of questions can be asked from here. So my sincere request to you, please go through this. Okay. The next method is addition of halo acids to alkenes and addition of halogen to alkenes. That means starting material is alkene. Both the reactions we have discussed in the chapter hydrocarbon while doing alkene. So I don't think I need to discuss a lot more. So you know, when we have alkene, symmetrical or unsymmetrical, when we add halo acids, the addition takes place across the double bond. Since it was a symmetrical alkene, you can add H wherever you want, Cl wherever you want across the double bond, and the product which you got here is CH3, CH2, Cl. But when the alkene is unsymmetrical, as I have mentioned earlier, it's a very important rule. You have to remember Markovnikov's rule, which states that during an addition reaction of an unsymmetrical addendum, out here it is HX, to an unsymmetrical alkene, the negative part of the addendum goes to that unsaturated carbon having lesser number of hydrogen. So let us try to understand again all over again. It's a repetition for you, it's nothing new. You look here, this is the alkene we have, which is very much unsymmetrical. This carbon, these two carbons are unsaturated. I have nothing to do with this. Okay. So this unsaturated carbon has how many hydrogens? 1. The first one is having 2, second one is having 1. So what is the negative part of the addendum here? The negative part is Br and positive part is H. Okay. So if I do anti-Markovnikov's addition, as you can see here, it's written in presence of peroxide. If I do anti-Markovnikov's addition, then Br will go to carbon containing more hydrogen and H will go to carbon containing more hydrogen. And if I do Markovnikov's addition as we have done here, Br will go here and H will go here. So that's how we get two different products depending on what reagent is added. And as you know, anti-Markovnikov product is exclusively for HBr. No other halo acid can be added according to anti-Markovnikov rule. I am not spending much time on this because this I have discussed earlier. I have sent you the video also. If you wish, you can listen to the video all over again, watch the video all over again. Addition of halogen across the double bond, across the alkene, is mainly for addition of chlorine and bromine. Okay, usually no other halogen is added like fluorine and iodine. Here we need a solvent, carbon disulfide and carbon tetrachloride. Across the double bond, the halogens get added up across the double bond and we get a vicinal dihalide. If you remember, we have discussed there are two types of dihalide. One is vicinal, another is geminal. Vicinal dihalide means the two halogens are attached to the neighboring carbons. And when you add bromine to this particular reaction serves as an important tool to identify unsaturation. That means to understand whether a given compound is saturated or unsaturated, we add bromine, which is having a reddish brown color, in carbon tetrachloride, and if the brown color of bromine disappear, then we can understand the given compound is unsaturated. The last method is halogen exchange. In halogen exchange method, what happens? You already have a haloalkane, but you want to replace the halogen by a halogen of your choice. Such reactions are called halogen exchange. So here we can prepare iodoalkane. This method is most suitable for preparing iodoalkane, where your starting material could be chloroalkane or bromoalkane. And the reagent is sodium iodide or potassium iodide, and the solvent is dry acetone. Now question can be asked, what is the importance of it? What is the significance of using dry acetone here? So as you can see here, from here NaCl will be lost. NaCl will be lost as the byproduct, and what will be left outside the box? What will be left outside the box? RNI. So RNI will be the product formed. Okay. Now you may notice here in NaCl I put a down-headed arrow. Now what does this down-headed arrow mean? The down-headed arrow means it is solidifying. That means it becomes precipitated. It is insoluble. Similarly, if we take RBr and you add NaI, same thing will happen. Ri and NaBr will be formed, and NaBr being insoluble in dry acetone, so this also will precipitate out. Now, what is the importance of using dry acetone here? This question can be asked. You see, we know that organic reactions are very slow reactions, and after a certain period of time they attain equilibrium. That means no forward or backward reaction takes place, or in other words, rate of forward reaction becomes same as rate of backward reaction. So as a result, the reaction product which we desire to prepare doesn't form in large quantity. That is why what is done, we try to make such arrangements where the equilibrium is disturbed according to Le Chatelier's principle. So here the moment sodium chloride and sodium bromides are precipitating out, they do not take part in the reaction anymore. So it is assumed that we are removing the product formed from the reaction mixture, which facilitates the forward reaction. So more and more reactants will react to give you the product. As a result, you will end up with a good yield. So that is the importance of using acetone. Okay, so acetone is a non-polar compound, and sodium chloride and sodium bromides are polar compounds, and we know that like dissolves like. So non-polar solvent will not dissolve polar compounds, so they will precipitate out. I hope it is clear. The last method is Swartz method, and this particular method is exclusively for preparing fluorocompounds. You might have noticed so far none of the methods could give us fluorocompounds. So this is the only method by which fluorocompounds can be prepared, and the fluorinating agents are silver fluoride, mercurous fluoride, cobalt fluoride, and antimony fluoride. So if you are asked to prepare fluoroalkane or any conversion is asked, you may use any of the reagents depending on what is your starting material. So here you see I have taken Rx. Rx could be RCl, RBr, Ri, whatever. When we treat it with silver fluoride or any of these reagents, then what we get is fluoroalkane, and together with the, if I take silver fluoride, then the other silver salt will be formed. Suppose if it is RCl, then here it will form AgCl. So that is all about the preparation of haloalkanes. The next will be preparation of haloarenes, which I think I have already posted the video on that.